somewhere in the depths of space, far beyond the planets we know, far beyond where sunlight shines bright enough to light up a day. Two tiny spacecraft continue their endless journey through the cosmic void. Their Voyager 1 and Voyager 2 launched way back in 1977, when humanity decided to send messengers into the cosmos, hoping that someone, somewhere, in the vast expanse of the universe, might find them. Picture this: September 5, 1977, at Cape Canaveral, a Titan Centaur rocket roars to life, carrying Voyager 1 into the sky. Just 16 days earlier, her sister ship, Voyager 2, had already begun her journey. These weren't just scientific instruments. They were our ambassadors, carrying golden records with sounds and images of Earth, messages from world leaders, music from Bach to Chuck Berry, and greetings in 55 different languages. These probes left the orbits of every known planet decades ago. Years ago, they crossed what we call the heliopause, that invisible boundary where the solar wind, that stream of charged particles flowing from the sun, finally loses its epic battle against the interstellar medium. And yet, here we are tonight, questioning something that seems to contradict everything we've been told about these historic missions. The question is simple, but the answer is deeply, profoundly unsettling. Have they really escaped the solar system, or are we witnessing one of the greatest illusions in the history of space exploration? Because it turns out, despite all the headlines celebrating their triumphant exit into interstellar space, despite the press conferences and the jubilant scientists, despite everything we've been told, the Voyagers are still trapped. They're still prisoners of an invisible cage that extends far, far beyond what anyone imagines. And when you understand the true dimensions of this cosmic prison, when you grasp the real extent of the sun's gravitational embrace, your entire perception of these heroic journeys will change forever. Welcome to tonight's exploration, where we'll uncover the mysteries of the universe with patience, precision, and data. If you enjoy this kind of deep dive content and want to keep discovering the most fascinating secrets of the cosmos, don't forget to hit that subscribe button and turn on notifications. Today, we're going to dismantle one of the most repeated myths of the space age, and we'll do it with patience, data, and the calm that great revelations deserve. So settle in, because this journey is going to challenge everything you thought you knew about the boundary of our solar system. To truly understand why the Voyagers can't escape, we first need to appreciate what they've already accomplished. Because make no mistake, these spacecraft have achieved things that seem almost impossible, even by today's standards. The Voyager missions were born from an extraordinary realization. In the early 1960s, a young aerospace engineer named Gary Flandreau discovered something remarkable: a rare alignment of the outer planets that occurs only once every 175 years. This alignment would allow a single spacecraft to visit Jupiter, Saturn, Uranus, and Neptune using gravitational assists, essentially using each planet's gravity as a slingshot to the next destination. It was called the Grand Tour, and the launch window was narrow. The late 1970s. Miss it, and humanity would have to wait until the 22nd century for another chance. NASA seized the opportunity. The Voyager spacecraft were engineering marvels, each one weighing about 25 kilograms, powered by plutonium-238 radioisotope thermoelectric generators, because solar panels would be useless in the dim light of the outer solar system. They carried cameras, spectrometers, magnetometers, and instruments designed to study everything from planetary atmospheres to cosmic rays. Voyager 1's journey took it past Jupiter in March 1979, revealing active volcanoes on the moon Io, the first volcanoes ever discovered beyond Earth. Then came Saturn in November 1980, where it took stunning photographs of the planet's rings and discovered the thick atmosphere of Titan, Saturn's largest moon. Voyager 2 followed a different path, After Jupiter and Saturn, it became the first and still the only spacecraft to visit Uranus in January 1986 and Neptune in August 1989. The images it sent back revealed worlds stranger than anyone imagined. Neptune's great dark spot, Uranus's tilted rotation, Miranda's fractured surface that looked like a world broken and reassembled. These encounters weren't just photo opportunities. Each gravitational assist accelerated the spacecraft, stealing a tiny fraction of the planet's orbital momentum. By the time Voyager 2 left Neptune, it was traveling at approximately 17 kilometers per second relative to the Sun, over 61,000 kilometers per hour. That's fast enough to circle the Earth's equator in just over 2 hours. Fast enough to reach the Moon from Earth in less than 6 hours. Fast enough that if you could maintain that speed on Earth's surface, you could travel from New York to Tokyo in less than 10 minutes. And yet, in the context of truly escaping the solar system, this incredible speed is heartbreakingly, almost tragically slow. Let's take a step back and think about what escape really means in the context of gravity and space travel. When we launch something from Earth, a rocket, a satellite, a spacecraft, we're fighting against our planet's gravitational pull. Earth's gravity wants to pull everything back down to the surface. To permanently escape this pull, you need to reach what physicists call escape velocity. For Earth, that escape velocity is about 11.2 kilometers per second, roughly 40,000 kilometers per hour. Anything that exceeds that speed can break free from Earth's gravitational embrace and drift away forever, assuming no other forces act on it. The Voyagers exceeded that barrier long ago, in their first few minutes of flight. But here's the first critical problem that most people don't grasp. Escaping Earth doesn't mean escaping the solar system. Not even close. The Sun is an entirely different beast. Our star contains 98.86% of all the mass in the entire solar system. Let that sink in for a moment. All the planets, all the moons, all the asteroids, all the comets, every speck of dust in the entire solar system, combined makes up less than 0.14% of the total mass. The rest is the Sun. That enormous mass creates a gravitational well that extends much, much farther than most people realize. The Sun's gravitational influence doesn't stop at Neptune or Pluto. It doesn't stop at the heliopause. It extends outward in an invisible sphere that encompasses a region larger than most people can comprehend. To truly break free from the Sun's influence, to achieve escape velocity from our current position here on Earth, you would need to travel at approximately 42 kilometers per second. That's almost 4 times faster than Earth's escape velocity. The Voyagers, at their maximum speed, barely touched 17 kilometers per second. That's less than half of what's needed for true solar escape. Now, you might be thinking, but wait, the Voyagers are much farther from the Sun now than we are. Surely at that distance, the escape velocity is lower, right? And you'd be absolutely correct. Escape velocity does decrease with distance from the Sun. In fact, it decreases with the square root of the distance. At Neptune's orbit, for example, escape velocity is only about 7.7 kilometers per second, well below the Voyager's speed. So the Voyagers should have escaped, right? Here's where the cruel mathematics of orbital mechanics reveals itself. While escape velocity decreases with distance, the Voyager's speed has also decreased. Because even though the Sun's gravitational pull becomes weaker with distance, it never disappears, never sleeps. Every single second of every single day, for the last 48 years, the Sun's gravity has been pulling on the Voyagers, slowing them down. It's an infinitesimally small deceleration, mere fractions of a millimeter per second per year. But it's relentless. It's like trying to roll a ball up a hill that never ends. Even if the hill gets gradually less steep as you climb higher. As long as the ball keeps slowing down, there comes a point where it might not have enough momentum to continue climbing forever. This is the race the Voyagers are running, a race against gravity itself. And here's the uncomfortable truth that most space enthusiasts, don't want to acknowledge. It's a race the probes might be destined to lose. August 25, 2012, NASA held a press conference that made headlines around the world. The announcement: Voyager 1 had entered interstellar space. It had become the first human-made object to leave the solar system. The world celebrated. Scientists toasted with champagne. News outlets proclaimed that humanity had finally, definitively, sent something beyond our cosmic neighborhood into the vast ocean of space between the stars. But that celebration was based on a very specific, and, if we're being honest, technically misleading, definition of what constitutes the edge of the solar system. Let me explain what actually happened in August 2012. The Voyager spacecraft carry instruments that measure charged particles, the solar wind streaming out from the sun, and cosmic rays coming from interstellar space. For years, Voyager 1 had been detecting fewer and fewer solar wind particles and more cosmic rays. Then, quite suddenly, the solar wind particles essentially disappeared while cosmic ray detection spiked dramatically. Voyager 1 had crossed the heliopause, the boundary where the solar wind can no longer push back against the pressure of the interstellar medium. This is a real, measurable boundary. It's the edge of the heliosphere, that bubble of solar influence that the sun blows around itself like a protective shield. Crossing it meant Voyager was now bathed in the interstellar medium rather than the solar wind. By one definition, a magnetic and particle definition, Voyager had indeed entered interstellar space. But here's what that definition conveniently ignores: the heliopause is a magnetic boundary, a particle boundary, but it is absolutely, categorically not a gravitational boundary. Think of it this way: imagine you're in a house with the heating on. The warm air extends to the walls of the house. Beyond the walls, outside, the temperature drops. You could define the RJ of the house's thermal influence as those walls. But what if the house is on a large property, and the property is surrounded by a fence 100 meters away? You could step outside the house, feel the cold air, and technically be outside the house's thermal zone, but you're still very much on the property. You haven't left the owner's land. The heliopause is like the house walls, but the sun's gravitational property, its true domain of influence, extends far, far beyond, to a fence so distant that the house seems like a tiny speck in the center of a vast estate. The real edge of the solar system, the true gravitational boundary, where the sun's gravity finally loses its absolute dominance, lies much, much farther out than the heliopause. We're talking about distances that make the Voyager's current journey seem like barely the first step of a walk that will last tens of thousands of years. We're talking about a region of space so vast, so populated with objects still trapped by the sun's gravity, that it makes everything we commonly think of as the solar system seem almost insignificant by comparison. In 1950, a Dutch astronomer named Jan Oort was studying the orbits of long-period comets, those icy visitors that appear in our skies once every few centuries or millennia, before disappearing back into the darkness. He noticed something peculiar about their orbits. These comets seemed to come from random directions in the sky, not from the plane where the planets orbit. And their orbital paths suggested they originated from an enormous distance. Much, much farther than any planet. Oort proposed the existence of a vast spherical cloud of icy objects surrounding the entire solar system, a cosmic reservoir of comets extending from roughly 2,000 astronomical units to perhaps 100,000 astronomical units from the Sun. Abbreviated AU is the distance from Earth to the Sun, about 150 million kilometers. So 2,000 AU is 300 billion kilometers, and 100,000 IU, that's 15 trillion kilometers. Let me give you some perspective on just how vast this is. If we built a scale model where Earth was just 1 meter from the Sun, the planet Neptune would be about 30 meters away. Pluto at its farthest would be roughly 50 meters away. The heliopause, where Voyager supposedly left, the solar system, would be somewhere around 120 meters. But the Oort cloud, in this same scale, the Oort cloud would begin at 2 kilometers away and extend outward to 100 kilometers. Imagine standing at a point and knowing that for 100 kilometers in every direction, north, south, east, west, up, down, that entire sphere is still part of your solar system. The Oort cloud is estimated to contain billions, possibly trillions of icy objects. Most are small, just a few kilometers across, essentially giant cosmic snowballs made of frozen water, methane, ammonia, and other volatiles left over from the solar system's formation 4.6 billion years ago. These objects aren't just drifting randomly through space. They're gravitationally bound to the sun. They orbit our star in incredibly long, incredibly elongated orbits that can take millions of years to complete. Every once in a while, something disturbs one of these objects. Maybe a passing star's gravity tugs on it, or the gentle tidal forces from the Milky Way galaxy itself nudge it slightly. When that happens, the object can fall inward toward the inner solar system. As it approaches the sun and heats up, it develops the spectacular glowing tail we associate with comets. It swings around the sun, perhaps giving sky watchers on Earth a beautiful show, then heads back out to the distant reaches from which it came, not to return for thousands or millions of years. These are the long-period comets, visitors from the Oort cloud. And here's the crucial point. As long as these objects remain gravitationally bound to the sun, as long as they continue orbiting under its influence, they are part of the solar system by any reasonable definition. And the Oort cloud is where those objects live. Billions of them, all still very much under the sun's gravitational control, all still part of our cosmic neighborhood. So let's bring this back to the Voyagers. As of 2025, Voyager 1 is approximately 165 astronomical units from the Sun. Voyager 2 is about 138 AU away. They're moving at roughly 17 kilometers per second and 15 kilometers per second respectively. These are the most distant human-made objects in existence. No human creation has ever been farther from home than these two spacecraft. They're over 20 billion kilometers away, a distance so vast that radio signals, traveling at the speed of light, take more than 22 hours to reach Voyager 1 and return. When NASA sends a command to Voyager 1, they have to wait almost 2 full days for confirmation that the command was received and executed. These spacecraft are so far away that the sun, from their perspective, is just another bright star. No longer a disk, just a point of light. These numbers sound absolutely staggering until you compare them to the true scale of the solar system. The Oort cloud approximately 2,000 AU, the Voyagers, at 165 and 138 AU respectively, haven't even reached 10% of the distance to the cloud's inner edge. Think about that. Despite traveling for 48 years, despite achieving speeds that no other human spacecraft has matched, despite crossing the heliopause and entering interstellar space by the particle definition, the Voyagers haven't even reached the beginning of the solar system's true gravitational boundary. They're in what scientists call the interstellar medium, space that's technically between the stars, in terms of its composition and particle environment, but gravitationally, they're still firmly in the sun's domain. It's a cosmic limbo, a transitional zone where definitions become blurred and uncomfortable. By one measure, they're in interstellar space. By another, more fundamental measure, the gravitational one, they're still in the solar system and will remain there for thousands of years to come. The Voyagers are like travelers who've left the well-lit streets of a city, walked beyond the streetlights, and now wander in the darkness beyond. They can no longer see the city lights clearly, and they're surrounded by the darkness of the countryside, but they're still very much on the city's land, still within its borders, even if those borders are unmarked and far from the city center. And now we come to the most sobering calculation of all. How long will it actually take for the Voyagers to truly escape?